We are now going to welcome our panelists for our first session to come up, focusing on new regional climate science, including on rainfall, water temperatures, and key climate science takeaways. Our panel includes Mark Thompson, Doug Marcy, and Dr. John Stam. Mark Thompson is a research associate with the Sanibel Captiva Conservation Foundation in their marine lab. Prior, he has worked as an engineer for private industry, and then joined the Marine Resources Research Institute. He subsequently moved to the Florida Department of Environmental Protection, where he monitored and analyzed southeastern Florida's waters using biological, chemical, and physical indicators. Mr. Thompson received his BS in Environmental Engineering from Purdue University and an MS in Environmental Science from the College of Charleston Medical University of South Carolina's Joint Graduate Program. Doug Marcy is the Senior Coastal Hazard Specialist at the NOAA Office of Coastal Management in Charleston, South Carolina. He has been with NOAA 23 years, working on flooding and sea level rise geospatial mapping projects, storm surge assessments, and coastal hazards assessment projects, contributing to more disaster-resilient communities. Mr. Marcy worked as a hydraulic engineer with the U.S. Army Corps of Engineers, Charleston District, and prior to that, at the South Carolina Office of Ocean and Coastal Resource Management. He has an MS in Marine Geology from the University of North Carolina at Wilmington and a bachelor's in geology from the College of Charleston. Finally, Dr. John Stam is a supervisory hydrologist with the U.S. Geological Survey's Caribbean Florida Water Science Center, serving in that role since 2015. From 2008, when he joined USGS, to 2015, he worked in the South Dakota Water Science Center, where his research included climate modeling, hydrology, and geomorphology. Prior, he served as a faculty member at California State University, Monterey Bay, and Western Colorado University. Dr. Stam received his bachelor's in geology from the State University of New York and his master's in geology from Pennsylvania State and his PhD in applied geology from Kent State University. The Menti will be open throughout the entire session, so please feel free to enter questions as you think of them, and they will be collectively reviewed and responded to at the end of the presentations. And with that, I'm going to turn it over to Mark to start us off.
Hello, I'm Mark Thompson. I'm with SCCF Marine Lab. I'm a research associate there. I'm going to talk to you today about a possible link between seagrass loss in the Ding-Darling National Wildlife Refuge and climate change. Right. That way.
That way and the down.
Okay, thank you.
Or maybe
Oh, down?
yeah. Down.
All right, sorry. All right, we monitored 13 sites within Ding-Darling National Wildlife Refuge for seagrass annually in May. We've been doing this since 2011, and we also have several continuously monitoring, continuous water quality monitoring sites within the refuge itself too. We have transects, we have quadrat locations, we look at density cover, canopy height for the seagrass. What we've been noticing lately that has really brought a concern to us is that we've lost most of our haliduli at our back base sites, our shallow water sites. We had densities of thousands of haliduli per square meters, and now those sites are 0 to a few sites still have tens per square meter. So it's a drastic loss of haliduli. So one of the things we thought of, or we were trying to look at was, is there some relation to climate change here? We looked at the water temperature at our continuously recording site nearby, and we analyzed 8,760 hourly water temperature points for each year and plotted them against time, and we found that this pretty strong increasing trend at our site in the wildlife refuge. To back that up, we looked at DEP's water quality monitoring sites in Estuary Bay and in mid-Matlacha Pass, and we found almost exactly the same trend going on there. Over the 12 years that I looked at the data, we saw an average of about 1.1 degrees C rise in mean hourly water temperature. Okay, so could this loss of halidouli be somehow linked to water temperature rise? So we looked at water temperature and halidouli together, halidouli density together at our shallow water sites, and before 2015 didn't see much, but after 2015 we saw a pretty strong correlation between halidouli loss and rising mean hourly water temperature. Okay, let's see. Yes. So we were wondering if this was a shallow water thing. We also looked at our mid-depth and deeper sites and found the same kind of pattern going on with tilapia. So that gave us something else to think about. We're not just, maybe it's not just a shallow water thing that's going on. We also looked at South Florida Water Management District's 2008 through 2021 seagrass aerial surveys, looked at changes, and what we found in Matlacha Pass, which is kind of a similar bay area as the wildlife refuge, we found that, especially from 2014 to 2021, lots of seagrass loss. If you're looking on this map here, the dark areas are where we have total seagrass loss. The lighter orange areas are seagrass loss. And the green areas are where you see seagrass increases. So it looked like there's something going on, you know, outside of the refuge, more regional. We also looked at Estuary Bay, found the same thing going on, maybe not the same aerial extent as Matlacha Pass, but there was quite a bit of seagrass loss and decreases in seagrass compared to increases in seagrass. And of note, when we were looking at these aerial surveys, we looked at the areas where we had total seagrass loss in the refuge, which are right here, and the aerial survey suggests that predict that there was increasing seagrass coverage going on there, which was wrong. So anyway, there's definitely some interpolation going on there. We wanted to see if maybe the temperature increases were directly affecting the loss of halidouli at our shallow water sites. Looked in the literature, you know, maybe you can start getting direct effects on halidouli from 36 to 40 C, which is pretty hot. We looked at our data, and we found that we had some periods of time where temperatures were above 33, and some shorter periods of time where it was above 36. So anyway, an 8th grade microcosm project at our marine lab looked at control 33 and 36 effects on halidouli for a month. We didn't have month exposure times shown in our data or anything, but we did it for a whole month and found there wasn't any difference in halidouli health after those periods, after a month period of time. So that made us think about maybe this isn't a direct temperature effect on the halidouli. So is it some kind of effect caused by maximum temperatures? Are they increasing over time? And we didn't have enough data really to even analyze it. Anything above 35 that might really be affecting halidouli. So we found no trends, not much going on above 35. So we started thinking this is probably not a direct effect of temperature on the halidouli seagrass. However, what we had noticed and had been seeing is this conversion in our shallow water sites of halidouli to Caulerpia fastigiata. At the end of our study period, we had complete conversion of our halidouli sites to the Caulerpa. So we wanted to look at, okay, the macroalgae Caulerpa and Cladophora in relationship to our halidouli density and in relationship to temperature. And we found, a strong positive correlation with temperature for increasing macroalgae cover and a fairly strong inverse relationship between algae cover and halidouli density. And when we looked at Thalassia, we also found these same relationships. So even at our deeper water sites, we were seeing macroalgae moving in where Thalassia once was. So let's look at the Caulerpa and Cladophora a little bit, relationship with temperature. From literature, we see that temperatures below 17 probably impedes the growth of Caulerpa, whereas maximum photosynthesis occurs between 24 and 35. So with that in mind, I analyzed the temperature data. Anyway, I analyzed the temperature data for our sites and for the DEP sites in Malachet and Estero and found that there were a pretty significant and decreasing trend in number of hours below 17, but a very strong increasing trend over time in the number of hours in the maximum photosynthesis range during our study period. So right now, climate seems to be providing that Florida Chamber of Commerce type weather for macroalgae. So we also looked at nitrogen and phosphorus and chlorophyll A at our sites where we were seeing all the effects. And there is some slight increasing trend in both TP and TN. Our chlorophyll data is kind of wishy-washy, not really seeing any kind of a trend going on there. And loads coming down the Caloosahatchee River, which impact us pretty often, over that course of the study period, there's a weak increasing trend in those loads for both TP and TN also. So in summary, we experienced the loss of most of all of our halidouli at our shallow water sites in the Ding-Darling National Refuge. We saw a significant decrease in Thalassia at mid-depth sites, and we saw a significant increase in mean hourly temperature over our 12-year monitoring period, along with DEP's two sites at Malachet and Estero. And analysis of the acute temperature data frequency and duration suggests it's likely not a direct temperature impact that's producing these losses. But we had a significant increase in macroalgae cover, especially Caulerpa fastigiata, at our seagrass loss sites. There was a significant increase in number of hours in the optimal photosynthesis range for Caulerpa growth. Plus, we had, a weak increasing trend in TNTP at our NWR stations. So, in conclusion, the loss of tillandsia and our Halidoulia and tillandsia at our NWR sites, likely a combination of environmental effects, including, increase in annual temperature, the increase in macroalgae cover, possibly increase in nutrient concentrations, and there could be many other things going on, changes in the tidal flushing due to climate change. We saw a significant increase in annual hourly water temperature over the study period, and we suggest this has an indirect detrimental effect on seagrass at our monitoring sites. One thing we need to look at more closely is the actual temperatures at our shallow water monitoring sites. Our water quality monitoring equipment is located in deeper points in our system, so they're usually about 1 meter deep or so, whereas our shallow water sites, they can be uncovered at low tides often. So we are going to look at getting temperature sensors out at those shallow water sites to actually see how hot it can get out there. So with that, thanks a lot.
Okay, I'm a tall guy, so I got to do this. All right. Good morning. Thank you, Jennifer, for inviting me. I'm honored to be here. I am one of the people that did travel from out of state. I live in Charleston, South Carolina. We're ground zero as well, especially for sea level rise. I'm looking forward to talking to you today about it, where we're going with some of the science. I'm going to start out at kind of like the global scale and a little bit of climate change 101, and then get into actual regional and local impacts here in Florida, and some tools that we are working on to try to address some of the issues that we have heard this morning. I did change the title a little from what was originally put in as an abstract. So I am going to talk about climate change, regional sea level rise impacts. And went the wrong way. We were talking about this morning, the IPCC. Jennifer's opening addressed this. That's the group that basically works on every 5 or 6 years. They do a whole modeling called CHNEP. We're on CHNEP 6 at this point, and they put out an assessment report. The 6th report came out, and we follow along in this country with the National Climate Assessment. It's sort of on that 5-year cycle. We take the latest and greatest climate modeling from the IPCC, and then we address that here in this country with the climate assessment, which just came out, NCA 5 came out a couple months ago. So everything I'm going to tell you today about the sea level rise science that came out in 2022 has already been incorporated into the National Climate Assessment. And you can see here that glasses help. We're experiencing the highest CO2 concentrations we have in the last 2 million years. We've seen sea level rise, the rates faster than we've seen in the last 3,000 years. In fact, sea level's been pretty steady for the last 4,000 years or so, and we're really starting to see that rise. Sea ice is at its lowest level in 1,000 years, and the glacier retreat is unprecedented, more than in the last 2,000 years. These are pretty staggering numbers. This is right at the beginning of the report. And so I thought I'd start off with scaring everybody to death. But no, So when you get down to what's going on in the United States, you know, this is, again, borrowing from the NCA 5. This is just observed temperature and precip. And I think we're going to get more into precip discussion. I won't get into that too much, but what we're really seeing is the dry areas are going to get drier, the wet areas are going to get wetter, the places that are already hot are going to get hotter. And you can see here, you know, down in the Florida area, that's pretty dark red. So we have seen increases in temperature, and all this goes together. We're also seeing observed changes in sea level. In most places, we've seen about a foot of sea level rise in the last 100 years, but it's not uniform. You can see the different color dots there. A lot of it has to do with what's going on in your location regionally with ocean currents and also vertical land motion. So you see up there in Alaska, we actually have tectonic uplift. Some places up in the Canadian Shield are rebounding after the Ice Age. So that's mitigating some of the sea level rise, but other places like Louisiana, you're seeing incredible rates of like 3 feet in the last 100 years due to subsidence. So the real question is, when we do the climate modeling, is what is the future temperature going to be? Because that really drives the whole system. It's really about the atmospheric temperature. The way they do that is a series of what's called scenarios. These SSPs, they're socioeconomic pathways. And what they are is basically different assumptions about how much greenhouse gas we're going to continue to emit, or whether we're going to curb that. It's also about population, you know, a lot of different factors, essentially. But it gives you a range of temperature, and then correspondingly on the right there, you see these dials, and that basically is the different SSP scenario. That'll determine when we're going to cross that 2-degree threshold that we think is going to cause major problems. So obviously the lower scenarios there, we may never cross that scenario, but the upper ones, we're going to do it a lot sooner. And again, that's driving the whole system. And then when it comes to sea level change, this is a complicated graphic, but I did kind of do that on purpose. This is from a paper by Oppenheimer. There are a lot of factors involved in sea level change. It's not a simple system. You know, you have everything from the expansion of the ocean because it's warming. Any liquid that you warm is going to expand. But there's a lot of interactions at the coast with you know, things like the Gulf Stream on the East Coast slowing down. You have vertical land motion, you have hydrology and groundwater extraction. I mean, there's a whole host of anthropogenic and natural variables. And then with extreme sea level, that little circle there, that's in any given storm situation. We may have even higher water levels on top of that with waves and damaging storm surge. So what is the greatest source of uncertainty with sea level rise? Well, you saw there was a bunch of scenarios there with the climate scenarios, but even more so, how fast the ice sheets are going to melt. Greenland and Antarctica is really one of the biggest, well, emissions, how much we're going to continue to put into the atmosphere, but CO2, but also how the ice sheets respond. So this idea, this is the Thwaites Glacier, is known as the Doomsday Glacier, kind of a cross-section. There's a lot going on where the warming underneath of this ice shelf is starting to erode back, and then the thinking is that once that calves, the ice will start to flow a lot faster, and that's going to increase the rate of sea level rise. And we are starting to see an increase in the contribution of Antarctica and Greenland, especially to the overall sea level rise question, where it was just steric, which is, you know, the temperature thing, is starting to be more increase in fresh water. And of course, the problem with that is there's the whole thing with density and freshwater versus saltwater, that can break down the whole AMOC current, and we've seen that in the past with a previous ice age. That completely shuts down, and that causes really big issues with climate change. There was a movie about it we were talking about. It could happen tomorrow or whatever. Yeah, I think that was a NOAA scientist. I'm trying to emulate Dennis Quaid today, but kind of a ridiculous movie as far as, like, you know, the troposphere's got to come down and freeze us all. Hopefully that won't happen. But So if you're looking at sea level scenarios then, they kind of pair them with what's going to happen with the temperature. So the SSPs are sort of there over on the right, different warming scenarios, and then the sea level projections are sort of, we laid that on top. And you can see, you know, it is a big range, and we'll talk about that with the uncertainties and where we're trying to do better as far as looking at historical observations and try to extrapolate that out and see where we're going. This brings us to the report I was a co-author on. Came out in 2022, so it's a couple years old now, but it is good to hear. I think a lot of folks are, I think the previous speaker said they're incorporating those sea level projections into their planning. And there's a task force that we're part of. All the different agencies you see here are involved in that, that produce the sea level science in these reports. And the main takeaways is that we're going to probably see another foot of sea level rise. We've already seen a foot in the last 100 years. In a lot of places, we're going to see another foot in the next 30 years. So we're really ramping up the rate. You're starting to see the rates, instead of being a linear trend, they're starting to be a quadratic. It's starting to be a curve. And then, you know, on top of that, we're going to have more extreme tides and everything, which I'll go into. And we'll see this profound shift, and I think we've already started to see this profound shift. Just the discussion this morning about the number of storms and how storms are not behaving the same way. There's more water in the system. And when it goes out into the future beyond 2050, it really does come down to the emissions. If we can curb the emissions, we can reduce the likelihood of going above 2 degrees Celsius, and that will not cause sea level to completely stop rising, but it will mitigate that. And as I mentioned, you know, it's not going to be the same rate everywhere. You're going to see these hot spots, the Gulf Coast, especially Louisiana, but also along the East Coast. You see the reds there, and even Alaska on the North Slope, there have increased rates. So these projections get updated every 5 years along with a climate assessment. And we're on our, we're on our 5th cycle now, but the last one was in 2017, and you can see the dashed lines there were the 2017 projections, and the solid ones are the new ones. We're getting better in the near term at 2050. Those are all the uncertainty shrinking. So all of the scenarios there are within about a foot of each other at 2050. That's why we're pretty certain we're going to see about a foot of sea level rise in the next 30 years. But then as you go out, there's still a lot of uncertainty. And that's why there's a big spread at 2100. And the reason that is, as we go down, you know, go back into the past, we look at observational data. We have historic records from tide gauges all over the world. We have some tide gauges in the US over 100 plus years of record. We started using satellite altimetry in 1993. So that compares, you know, with they can put on top of the observations from tide gauges. And then we can start extrapolating that, which is exactly, NASA worked on that. They used the historical record and then extrapolate that out to 2050, basically, you know, doing a best fit. And that gives us sort of what trajectory we're on. And then then you go out in the projection space, emissions become really important, and so does the processes. And what we don't know is the uncertainty in the processes, how fast the ice sheets are going to melt. Is that going to be a linear thing, or is it going to be all of a sudden? And that's why the range is so big. And so somewhere in the middle there, you're going to see the mean, and any probability distribution would be the more likely outcome. So the lowest of those scenarios is probably really unlikely, and the highest is probably really unlikely. But when you're doing planning, we'll talk about that in a minute, but that comes into play when it comes into like your risk tolerance. Okay, so drilling down, here's some Fort Myers gauge. The gauge has been there since, I don't know the exact year, but probably 65 or 8. So not quite 100 years of record, but if you extrapolate that out, that's just a linear regression. All the ups and downs are the different cycles, interannual variability. But we've seen about 1.17 feet of sea level rise in the past 100 years, if you extrapolate that out. This is the NASA extrapolation, so you can see the observed extrapolation there in the middle, almost 1.4 feet, is between the intermediate high and the high scenario by 2050. So if you're looking for what scenario should I use, we're kind of looking at where we're headed. Now granted, there's going to be other cycles like the Atlantic decadal oscillation and things like that. It'll cause it to go up and down probably over 10 or 20 year cycles, but that gives you kind of an idea. And that's causing things to change in terms of how we're experiencing the flooding, not just during storms. This is a nationwide average here. So back in 2000, we had an average of 2 high tide flooding events a year. I know there's a lot more in certain locations, but that's sort of the average. In 2020, we've had an average of 4, and then by 2050, we're talking more like 25 to 75 days. So almost 20 times as frequent. And so that's going to cause, the point where every high tide we have is going to start impacting things. And we try to map that in our office. We have this layer, it's our sea level rise viewer, I'll talk about in a minute, but the red area there is what we consider minor flooding. That's when things start to, a lot of that is just marsh and low ground, but you can see the number of high tide flood events in this chart. We didn't have any, and then all of a sudden, in the last 30 years or so, boom, we're crossing over that threshold. So there was a threshold there that we weren't crossing over very much, and now it's starting to happen more and more. That's because more water's in the system. And we can look at sea level as not like all the other hazards. All the other hazards are going to continue to happen. We're still going to have hurricanes. We're still going to have all the issues with groundwater, but I look at sea level rise as an exacerbator or catalyst to the system. It's just like making things worse. It's increasing the flooding. We're putting waves on top of that. It's starting to infiltrate in the groundwater, saltwater intrusion, and obviously the habitat issues that we just heard about. That's causing that too. So it's a little insidious. It happens very slowly. It's not like you're going to, oh, run, there's sea level rising. But it is going to, over time, make the floodplain move landward, and this is something we're trying to work on in the government right now with this federal flood risk management standard. And the idea is we have to start addressing future flooding, not just your policy for your flood insurance for this year, but 50 years out. It's going to continue to expand. So people that are not in the floodplain now eventually will be. And of course, if we try to wall off, do seawalls and things like that to protect areas, which we will. Charleston is going through that right now, talking about building a seawall around the entire peninsula. Then we are just basically creating another mini New Orleans. We have to pump the water out. Exactly what I'm showing here, which is you have increased tides, water levels at the coast. It's all connected. Most of our coastal cities have gravity-fed stormwater systems. They weren't designed to have the opposite end, the outlet, have water almost higher than inlet. And it's based on, if you're an engineer, it's called hydraulic head. The bigger the difference in elevation between where the water goes into storm drains and where it exits, the faster it can drain. If you don't have what's called head, then it'll just sit there. So the extreme rainfall with high tides is causing a major issue. So in our office, we have a lot of resources. I would encourage you to go to NOAA Digital Coast. If you've never heard of Digital Coast, it's part of our office. Our office manages the National Estuary and Research Reserves. We have a coral reef conservation program. We also have Digital Coast. There's a coastal inundation page. That's all the references I was mentioning and access to tools. We do have a sea level rise viewer, which does mapping all the way up to 10 feet above mean high water. It has the latest projections in the tool as well as the 2017, so you can compare those. And you can download all the data that's behind it. It's a 3 meter resolution digital elevation models, and you can download all the projection information as well. We also have an application guide that was produced by a separate team than the technical author team. For the 2022 report, I would encourage you to go there. It's sort of a layman's version of the report itself is kind of dense and technical. This is more for practitioners. It's not really step-by-step instructions, do this, do this, do this, but it will give you kind of like the most appropriate way to use the data and answering these questions like what planning approach should you use, which scenarios should you use. And that's important because the scenarios you should use is really based on risk tolerance. So things that are critical infrastructure and things like that you want to be around or that can't fail, you're going to want to use a higher scenario for that and less for open space that doesn't matter if it floods every once in a while. So I'll leave you with this last one. We have a really good video. I was going to show the video, but that would have taken up 7 minutes of my time. So, and based on earlier, the videos are good luck with yours, by the way, coming up. Anyway, it's a really good takeaway from the report and everything I just told you in a graphical way, and it's really good if you want to educate other folks when you go away from the conference, like even school-age kids, they can get something out of this. So I will leave it there, and we'll do questions, I guess, after the panel's done. Thank you.
Well, Doug mentioned he was tall, and following Doug illustrates how short I am. Anyways, yeah, so I'm John Stam. And basically, I'm going to be talking about what the USGS, U.S. Geological Survey, has been up to in terms of research. The title of my talk is Estimating Historical and Future Rainfall Extremes for Florida. And this is work that we've been doing with the Florida Flood Hub. Jennifer mentioned the Flood Hub earlier on. And so we've been really involved with them on looking at rainfall extremes and how that affects flooding. You gotta kind of understand rainfall before you can understand flooding. I've got my name up here, but the people that are really doing the work, Michelle Irizarry Ortiz, she's done a lot of work on these extreme rainfall events. Jason Bellino, he's doing a lot of work with climate models that I'll show you a little bit later. And then we also work a lot with a guy we call Obe, and Jayantha Obe Sakara out of FIU. And he was hoping to be here, he couldn't be here. But anyways, he's kind of an honorary USGS person because we work with him so much. Let's see if I can get this. Oop, maybe the wrong one. Okay. So the outline of my talk, I'll be talking about the kind of 3 research directions that we're going. The first one is looking at extreme rainfall in Florida and looking at depth, duration, frequency, or what's called DDF curves of extreme events. A second part of our research with the Flood Hub, USGS research with the Flood Hub, is looking at what's called a reanalysis of Florida weather, looking at about a 45-year period. We want to see how well the kind of high-resolution models do for Florida. And then what's happening in the future, right? And we're going to be looking at warming scenarios, and I'll talk about that a little bit later on in the talk towards the end. Oop, I keep on going the wrong way. Okay, so DDF, depth, duration, and frequency. What do I mean by that? So I'll give you a little background here. So depth is really the depth of rain. How many inches of rain fell, right, in a storm, and over what kind of time period? What's the duration, right? How much rain fell? What was the inches of rain that fell over 1 day, or the total rain that fell over 3 days or 7 days? And Michelle, in her work, she's been looking at these duration events. So how much rain fell in a 1 day period, a 3 day period, a 7 day period? But then we're also looking at the frequency of these events, right? Does it occur on average once every 5 years, every 25 years, every 100 years? We're also looking at 10 years, 50 years, 200, a bunch of these different frequencies. And one way I want to twist this so you have a better understanding of what this really means is that if you have a 5-year event, basically in any given year you have a 20% chance that that's going to occur, 1 divided by 5, right? The 100-year event, basically every year there's about a 1% chance you're going to see that, right? So put that in that perspective. Now, you start looking at these rainfall depths and over these certain durations and having these certain frequencies by looking at weather station data, by figuring out what's going on in the historical record. What kind of rainfall events are we seeing? And so the work that we're doing is kind of started on by looking at what's called these NOAA Atlas 14 stations, it's what they're called, and looking at this period, 1966 to 2005. This is a map. I know this screen is a little bit hard to read sometimes, but these little red dots are showing where these stations are that Michelle used when she was doing her analysis of the historical depth, duration, and frequency of rainfall events. 174 in South Florida. And I'm really going to focus in on a study that she did. It's really for the South Florida Water Management District for South Florida. And you can see that Water Management District outlines up there. But with the Flood Hub, we're extending this to the entire state. Anyways, there's going to be a lot more stations, and that research is underway. OBE actually did some work on the entire state, and we're just kind of building off of that. Okay. The other thing is that, so you know these, historically what's going on over the past several decades with these extreme events, what's happening in the future? And so what Michelle has worked on is what's called a change factor. So in 2070, how much would these depth, duration, and frequencies, how much would the amount of rain, the depth change, right? So these change factors are computed for some time in the future. So let's say that the amount of rain that falls over a one-day period, the 25-year event, so a 4% chance that it's going to occur in any one year. Let's say that's 4 inches of rain is your one-day event that occurs once every 25 years on average. And then you compute this change factor is 1.25 or a 25% increase in this event. So if you want to figure out how much rain is going to be in the future for these extreme events, you just multiply out. So the one-day 25-year event is projected in the future to be 5 inches, right? 4 times 1.5. So that's just a little bit of background on kind of what we're producing of these change factors for how these events change in the future. So for South Florida, we have a report out. Now, by the way, on some of these slides, you'll see a little kind of disclaimer on here because a lot of this work is ongoing, but this is done, right? So there's this report by Michelle and others. I think I'm in the list too. Development projected depth, duration, frequency curves, centered on 2070, right? But using data over that period, 2050, 2089, to get these estimates for South Florida. Another report's going to be coming out at the end of the year for all of the entire state. And it's a U.S. Geological Survey report, so you can take a look at that to get the gory details of what's going on. And I tell you, it can get pretty complicated. One of the things when you're looking at how rainfall is going to change in the future is you need to have some kind of data to work off of. And you really need a climate model to work on. And there's a lot of different models out there at different resolutions, but they all have their roots on these global models. They all kind of go back to that and maybe massage those numbers and so on. So virtually all estimates of future climate are based on global scale models. And they're called Earth systems models. And they simulate the dynamics of the atmosphere and the ocean. They're solving equations, force equals mass times acceleration in a really, amped up form of that equation and so on, right? They're solving the hydrodynamics and the thermodynamics of the system, and they're doing the atmosphere, but they're also doing the ocean. They're solving ocean currents as well. And because they're doing the atmosphere and the ocean, they're called a coupled model. And you may have heard of a term CMIP 3, CMIP 5, CMIP 6 as these groups of models that people are looking at, coupled, modeled into comparison projects. So these are models that are simulating the atmosphere and the ocean together, right? Anyways, so we need these climate models to work off of to get our estimates. And here, for example, is the Community Earth Systems Model, CESM, that the National Center for Atmospheric Research puts out. Just an image. Looks like out in the Pacific there's a few hurricanes that it has spiraling around, so we can simulate that kind of resolution. This is one of the more recent models. Some of the older ones, this is one I worked with, CCSM3. This is the CMIP3, older version of some of these models. And because of computers' ability at the time, they had to represent, for example, North America in a simplified way. You could see the kind of the Rockies there. You can see the Appalachians a little bit and so on. And Florida's got a kind of a funky shape to it. But you got to work with these data. So here we are looking at these data that we can maybe use to estimate extreme events in the future, right? But that's Florida, right? We got 9 points, and how do we do that? How do we go from that to get something that's more usable for Florida? So what's typically done is what's called downscaling. And these are just some models. The names are kind of, there's a bunch out there. These are the ones that are commonly used. So this will go from a global scale model down to, for example, 6 or 4 kilometer resolutions. For these statistical methods, there's these other dynamical ones that 25, 50 kilometers, that's still pretty good, right? And 4 kilometers. Now, the two statistical models, what they do is they're basically taking the points that you have data at, right? And they're interpolating, right? And these are called, the CA on these things are called constructed analogs. And what they're trying to do is do something in a somewhat informed manner, right? And so they're just not interpolating, but they're saying, okay, let's look at weather patterns. If it's raining 10 miles from here, right, and I want to figure out what's going on at this point, if it's winter time, you got these big fronts coming. It's likely going to be raining here, right? So if you got a weather system that looks like it's a winter system, go ahead and put rain at your point when you're interpolating, right? But if it's summertime and you got rain that's 10 miles away, well, there's a good chance, it's not raining here because it's just a localized thunderstorm, right? I mean, it could be raining on the other side of the street and it's not raining here, right? So anyways, it uses these weather patterns to try to inform the interpolation and make it a little bit better, and that's what this constructed analog stuff. LO is for local, the MACA one uses really national. It looks at everything in the nation. The other models are called dynamical models. They're basically like the global models, just applied to a smaller area. They solve hydrodynamics, thermodynamics. The Cortex ones, they ran those a few years back, so they're still relatively coarse resolution. There's a company called Jupiter Intelligence that South Florida Water Management worked with that ran a model called the WRF model, WRF, and I'll show you that a little bit more. They got a 4-kilometer model, and that one actually, it's kind of a mix of statistical in that they simulated the current climate, and they said, well, the GCM say things are going to be like a little bit warmer, a little bit more wet, so they scaled up the current. Anyways, those are the kinds of things that Michelle used. You'll see LOCA, MACA, Cortex, and WRF in some of these slides. Before I throw the next slide at you, which you'll all go, oh my God, what's up there? I want to just kind of explain to you kind of how this next slide that you haven't seen yet is plotted up. And I use this box and whiskers plot. So it's kind of on the y-axis showing rainfall. And it's got this line in the middle of it. That's your median, that's your central value. And then and it's showing rainfall in the next plot. The rainfall estimated by all of these downscaled models. Like Local will have a bunch of downscale simulations he does based on a lot of different global models. But anyways, most of the values are going to be in the box, like 68% are going to be in there. There's going to be a few more that are in the tails that go down to the 5%, and then 95% are going to be that value and less. And then there's going to be dots that are showing outliers. So just to kind of show you this, and here's the slide that I wasn't sure if I really want to show you. A lot up there, right? This is just one of several of plots that are in Michelle's report. I just put up the 1-day duration. There's a 3-day and a 7-day duration. And what this has is, what is this change factor? In this case, it's a % change going out into the future centered around 2070. Right, and so on the left-hand side is your change, your % change. Let's see if I can show you this way. Yeah, so there's no change. You would have a reduction in these events, or they could be 100% greater or 200% greater. There's your 100% line, right? Here's these different models that I just talked about: Cordex, MACA, LOCA, and the Jupiter Wharf. And they're all kind of bunched together, like there's one set, there's another set right here. And this is the return period. So this is what these models say would happen in the future, that there'd be about a 15% for most models. Some of the ones are a little bit lower, right? Increase in that event out in 2070. And then as you get to these more extreme rare events, you can see this number goes, the box goes up. It's a little bit higher, bigger changes. A lot of this work is based on looking at like 45 years of data, so it's hard to actually estimate the 200-year event. Are you even going to see that in that record? Right. Anyways, one of the points of this, the Flood Hub is looking at this stuff. It's an awful lot to digest, and they're putting together a report that is going to kind of synthesize this down and say, okay, we'll provide you guidance on how to interpret this, and that should come out in a few months. We're also kind of looking at, okay, we got some models that are down here. They're saying, is that change? That's the LOCA is kind of saying a little bit of change. Some of the other ones are saying a lot. Is there something that we can do to get a better feel for, do we trust these models? And, oops, I'm shooting the screen with the laser pointer here. So the question in that last one was, what's the right value to use, right? Can we somehow reduce the variability and say, okay, we actually trust these sets of models more than others? And the issue is that these global models are too coarse to really represent the climate processes that are going on in Florida. You've got, small-scale thunderstorms, land use changes, coastal effects, and so on. So we're developing this high-resolution model that can capture these processes. We're going to back up here, and you see this, you look at this and you go, that's a weather map, right? A meteorologist would call this an analysis, a surface analysis. When you're looking at the weather in the past and using these climate models to simulate the details of weather in the past, it's called a reanalysis. So that's where this term reanalysis comes from, right? It's basically a weather map of the past, right? A dynamic model simulation of historical weather, often is simulating observations. So the model nudges to like, oh, we got weather balloon information that says this, so let's make sure we're kind of matching that kind of upper atmosphere pressures and moistures and so on. And the model is called the Weather Research and Forecast Model. It's basically the model that you see the TV stations use. So when they simulate out the next week, they're using WRF or a variant of WRF, right? And as I said, it's like these global models simulates hydrodynamics and thermodynamics. And it also simulates land processes. It doesn't do the ocean. We're simulating basically 45-year periods, so Michelle can have some data to look at, compare with her estimates of what the extremes are for the historical period. We're doing that at a 4-kilometer resolution, and then we're looking at specific events at 1 kilometer, the Fort Lauderdale event that just happened. And then if you have a hurricane that begins with the letter I, we decided to choose you also. And we're looking at completing these runs in this summer coming up. Now, this is the area generally that the model, I'm going to show some test runs, a little smaller area, but this is what we're looking at simulating. Florida and the extent of the area that's underlain by the Floridan aquifer system, which extends north to that black line. And then the watersheds that will eventually drain down and actually supply some water for the Floridan aquifer system. So these watersheds up here that drain far enough south to affect the aquifer. All right, let's see if this works. So this is, what I'd like to show you here is an animation of what happened on a few days starting April 9th up to 13th. Oh, there it goes. This is precipitation, here's the soil moisture, and here's air temperature. Oh, and you can see this is basically the front coming through. And one thing that I'll show you, we'll run this again for you so you can look, but you'll notice that where there's rain, it's cloudy, so it's a little bit cooler temperatures there. You'll also notice, that there's, you'll also notice that you get the soil moisture once you get the rainfall. So the rain is starting to organize, and here it comes up, and you can see the soil moisture starts to get wet, right? And then this comes up here, and you see the soil moisture get wet here, and you can see the clouds are making things a little bit cooler in that area. So this just kind of shows you what the kind of resolution that we're trying to get out of this stuff. If you could run that one more time, and just so we can watch air temperature, you can see it goes from night to day. It gets, warmer, the brown, to lighter. And you see the effect of clouds and the wet soils and so on. But that's the event, the initial runs of our event for the Fort Lauderdale at 1 kilometer. Okay, let's see if we go to the next slide here. Oh, sorry, I went too far. So this is just a snapshot of the Hurricane Irma, the hourly bands of rain. So there's the hourly stuff, and if you look at the total for the day, you see these bands kind of add up, and we've got this rain going all the way up and down the coast. Here's another animation, and if we could run this animation, you'll see Hurricane Emma. And this is total precip, so once it's going to keep it a running total. And here comes the hurricane, and it goes right up the coast. So this is the kind of stuff that we're doing to try to get better detail on what's going on in Florida. Okay, so we got this model, and we're kind of running it, and we're tweaking it, and we're making sure that we can get the historical right? Now let's think about, what about the future? And so the approach that the Flood Hub is taking, and we've been talking with the water management districts about this, is to go to this warming scenarios approach. There was a discussion Doug had about shared socioeconomic pathways, right? But we're actually not quite doing that. We're looking at, can we simulate the world at 2 degrees warmer if globally it was 2 degrees warmer, right? Can we simulate Florida in that case if it was globally 3 degrees warmer, and compare that to some historical period? Initially, we're proposing, this is work that's just starting, to look at 2011 to 2020 as the historical kind of baseline that we're comparing things to. So, for example, what would the climate of Florida be like in a 3-degree warmer world, right? So rather than saying what's it going to be like in 2050, let's just say, okay, what's it going to be like when it actually gets that warm out there? So here's, again, the IPCC kind of figure where you've got these changes in global air temperature from these different shared socioeconomic pathways going out from 1950 to, I think this case, it's 2015 is the historical black line, and then going out on these different pathways depending on what we end up doing in the future, right? On the left-hand side is the temperature change. If the zero line is kind of the average from 1995 to 2014, and so 2 degrees rise above that, 4 degrees, 6 degrees. On the right is looking at relative to the pre-industrial. So you see that zero line, the zero line goes down because we've had almost a degree increase in temperature since, right, from pre-industrial to until 1995, 2014, right? What we're doing here, instead of, trying to do one of these, just choose one of those, we're saying, okay, let's just look at, here's our historical period. What are things like at 2 degrees warmer or 3 degrees warmer? And some of these models get to 2 degrees faster than others, or 3 degrees faster than others. Some of them don't get to 3 degrees, right? So anyways, that's what we're doing these, choosing these. Maybe we'll do 1 degree, maybe we'll do 4 degree too, right? We're still kind of discussing that kind of stuff. Oop, I can point it this way and it changes too. All right, so we're working with Ben Kurtman out of the University of Miami, and he's running the global model and saying, okay, I'm going to run the global model where I'm going to keep things at 2 degrees globally and just simulate that over and over and over again, and it'll vary because of the noise in the model, and do a 50-year simulation of the world at 2 degrees, if it stayed at 2 degrees, or 50-year simulation at 3 degrees, and a 50-year simulation if it was at the average for that 2011, 2020 time period, right? So that's the kind of root, as I said, everything's rooted in these global models. This has got a 50-kilometer grid in the atmosphere and a 10-kilometer grid for the ocean. So it's a coupled model, right? But stuff that's going on in the Gulf of Mexico and so on, we want to get maybe some more details of the feedback there. So then we're going to, and that's going to feed into a regional model that Florida State is running, that Vasu Misra he's also involved in this work. And that has a 10-kilometer grid for the ocean, but also a 10-kilometer grid for the atmosphere. And so what we want to do is for example, how does the loop current, out there in the Gulf, or how does it, if it changes over time, how does that affect Florida? Florida is this wacky part of the U.S. where it's a peninsula sticking out in the ocean. We're really affected by the ocean, right? It's not that wacky. And so then that 10-kilometer stuff, we're trying to get into these finer resolution models, the WRF. We're doing the reanalysis to say that, yep, we can run it, we could get it set up so it's doing the historical right. Now that we know that's set up, let's take these models and try to simulate what's going on. And then look at that. And then compare that to all these other estimates that we had. Michelle can do her DDF curves off of this and say that, well, when we do this high-resolution model, we're actually agreeing with this subset of models. Maybe we can get a better handle on which one of that crazy graph I showed you earlier, on what part of that is more correct. Anyways, this is just starting, plan completion in about 2 years. We're kind of, I know Ben and Vasu were ready to start up on this stuff. So, in summary, we gave you an overview of what the USGS and the Flood Hub is doing on this stuff. We've been looking at extreme rainfall in Florida, these depth duration of events, and there's a lot of variability in these estimates, so we're trying to get a better handle on what numbers we can really rely on by looking at, first doing a reanalysis to look at historical Florida and the details, the weather in Florida, using the weather research and forecasting model, and it can capture these finer scale processes, looking at 1 and 4 kilometer scales. And then we're looking at just starting up these warming scenarios where we're simulating Florida's climate in a 2 and 3 degree warmer world. Maybe we'll do other things as well, 1.5 degrees or something. And the model spans from global to local scales, right? And then that output can be used to also provide another estimate of this depth, duration, frequency of these extreme events. And I'll just kind of finish off with that. I think I had another slide, but. All right, thanks.
All right, if you haven't already gone into Menti to put your questions, feel free to do so now. We're going to reveal them here on the, that's all right. I think one of the things you're seeing here is that, you know, this science is rapidly evolving. We're learning things both from reality, changes on the ground, like you heard with the seagrass and the macroalgae. We're also learning things that we are discovering through our efforts to incorporate science into these very sophisticated models that help us to better predict and understand what we can expect in the future. So I know that a lot of you have questions, and we're going to go, I'll try to pull this, to read some of these and pose them to our panel. So we have, how much did water quality improve when you allowed flow under your road? So if you could answer that.
I assume that is addressing the culverts that U.S. Fish and Wildlife Service. Okay. The culverts were placed under Wildlife Drive in the Wildlife Refuge 10, 12 years back. We actually, we saw better dissolved oxygen concentrations out there, but improvement in other water quality indicators, we didn't see much, really. Chlorophyll remains pretty high, and we still have this increasing trend in nutrients and all. So I would say it did not improve much at all, really.
If we could scroll down just a little bit so we can alternate some of these questions. So, is it, okay, most of these are for Mark right now. So let me see if I can find another one. Mr. Marcy, do you know of plans to prevent saltwater intrusion into the aquifers and drinking water? How bad is it already? Or will it move more to desalination technology? Is that part of, or if your analysis is looking at?
Oh, that's on, okay,
Yeah,
yeah. I briefly mentioned the saltwater intrusion issue. Our office doesn't really get into studying that. I think that's probably more of a USGS endeavor, but I know that especially with the Floridan aquifer, that a lot of the issue is the water table. Well, there's a couple issues. Yes, the salt water comes in kind of as a wedge, and of course the fresh water sits on top of that, sort of as a lens, and so that when the salt water comes in, it's actually going to raise the water table elevation, which is a problem because then it's going to expose water right at the surface because it's porous limestone. It's basically going to, so there's not going to, that's going to reduce the amount of infiltration that will be able to occur with rainfall events. But as far as drinking water and monitoring that requires monitoring wells and doing what's the specific conductivity to figure out the salinity. And I'll pass that to John. He probably can talk about that.
Yeah. Is this working? Yeah. Here we go. Yeah. We have a scientist in our Temple office, Jeremy Decker, who actually, he moved up from the Fort Lauderdale area and so on, and he did a lot of work with Broward County. Broward County is really looking at this kind of saltwater intrusion stuff, and one of the issues that they're dealing with is as the sea level rise or tides come up, they can extend up through the canals and get a lot further inland and affect things further inland in those flat areas with all those canals. So he's kind of modeling that, and how do you deal with the structures that are controlling those canal flows. So that's the kind of things that are being considered with the sea level rise. I know in Broward, we're still working with them on making a bigger groundwater model to kind of look at that issue down there.
Great. I can tell you from personal experience, I live in this area, and my well has gotten saltier to the point that it's starting to burn my plants when I irrigate with my well water. So definitely, I do believe that is already occurring in certain areas. All right, Doug? Oh, okay, go up one. Doug, some people will argue that 1 inch of sea level rise isn't a lot to worry about, will only affect beachfront owners. What would you say to open someone's eyes about the full impact of that change?
Is that 1 inch or 1 foot? I can't.
It might be 1 foot,
Okay.
actually. Sorry, my eyes.
Yeah, 1 foot doesn't sound like a lot, it depends on, when we talk about, because we do a lot of mapping of inundation, and it is all about, when it comes to inundation, it's all about elevation. Elevation is important, instead of location for realty, right? So areas like, the coast of Maine, where it's a rocky coast, there's a big elevation change. 1 foot isn't really going to flood that much. The flatter an area is, like this state, 1 foot can cover a really large area. Flat beaches, the rule of thumb is 1 foot equals 100 foot of inundation on really fairly flat beaches. So 1 foot up is going to go inland. And that's the whole idea with increasing the floodplain. When you add, a lot of what people do is, we just need to add freeboard, add to the base flood elevation at 1 or 2 foot. Okay, yeah, that's fine and elevation-wise, but when you map that out, the horizontal extent of the floodplain really increases. There's places like in Florida, St. Johns River, where it all happens within that 1 foot. 1 foot of inundation can really change the entire estuary system. So it really has to do with the flatness of the topography. So I would say, yeah, it's 1 foot, no big deal, but if you can imagine, we've built our infrastructure kind of right up to the mean high water line, maybe a little bit above that. You go to look at your docks and your piers and everything we have built, even our ports, which we rely on goods and services to come through our port system, are built at some threshold thinking that sea level is not changing, but every foot you add, you're going to start crossing over that threshold more and more and more and more. So the frequency of the events, just like with the rainfall, the frequency is going to start happening. It's going to start increasing, and then obviously the extreme events too are going to, so the whole frequency system is going to change. So the 1% storm or storm surge is eventually going to become the 10%. We're going to have that sort of magnitude storm is going to happen a lot more often because of that 1 foot change. Does that help?
All right, we have a question for Dr. Stam. Do new models go back and accurately predict previous extreme events hindcasting? How accurate are they? Ian dropped over 20 inches in Northport alone, flooding homes inland, not storm surge.
Yeah, I think one of my slides showed and I may have skipped past it, the Fort Lauderdale event, in which we got 30 inches of rain, and we simulated that one up, and we got it right in the right location, and the model said 26 inches of rain. And in that situation, if you went basically a kilometer or two away from the rain gauge, you would drop from 30 inches to down to like maybe 10 inches or something like that. It really dropped off fast. So we got some of these events, that's kind of the point. We're trying to get these events as accurately as we can. And that's what a kind of a reanalysis is it's trying to get that past weather simulated as precisely as you can, right? Now, when you're looking at the global models and projections, they typically do a historical run as well. But they're not trying to simulate precisely what the weather occurred in the past. They're trying to simulate what the historical climate was like. And then it's an experiment where you say, well, we got the climatology of the historical is in the realm of acceptable, and then we're doing an experiment where we're going to look at the future, right? So when you look at these global models and they do this historical simulation, you do have to do some bias correction on them to get those to kind of accurately predict those extremes. And that's one of the things that Michelle did. She had to do some bias correcting on these models, not reanalysis, but historical climate. And I guess the way I'll just back up here and say, like, think of doing a model of you walking your dog, right? That's what this kind of like this historical thing is. So I walk my dog, and I go down this street, and maybe a car goes by and we have to stop, or maybe my dog goes and sniffs this tree. What's the best model of me walking my dog that I just did? Well, it's me going out and walking my dog again, right? I'm the best model of that. But when I do it again, my dog might not sniff exactly that same tree, but it might sniff another tree. It's still sniffing a tree. I may not stop at that corner, right, for a car, but I might stop at another corner. I'm getting the behavior of climate correct, right? Getting the behavior of me walking my dog correct. So that's kind of that distinction between these historical simulations that the global models do to compare to the future versus a reanalysis, which you're really trying to get the day-to-day, the hourly to match as precisely as you can.
All right, we now have a question for Mr. Thompson. Did you also look at other potential climate impacts like salinity? Is that combo of salinity and heat leading to seagrass die-off in Florida Bay, could that happen here?
We mean to do that. We're still looking at data. That Florida Bay study was one that inspired us to begin looking at what's happening in our area. So yes, that is something that we intend to look more closely at, looking at the interaction of changes in salinity. We're right at the base of the Caloosahatchee estuary, and we can get some pretty crazy salinity swings even in the wildlife refuge. So it's an analysis that we are doing at this present time, but we really don't have an answer yet. Thanks.
All right. As a geologist, what makes you confident that sea level rise is caused by humans and not a global cycle? Are humans moving to naturally flooding areas?
I assume that's me. We're all geologists, so no, I can get that one. So there's two different things there. The first one, what makes us confident? As a geologist, you're right. We study in geology paleo sea level. We look at going all the way back to the Wisconsin and glacial period, which is about 14,000 years ago, and how sea level has risen since then. And we look at these cycles where you have increased CO2 for whatever reason. That was before man was even here. Mostly it was volcanic. And you'd had these cycles of about every 100,000 years or so, we'd have an ice sheet type situation, and sea level would go up and down. It's been as low as the continental shelf. It's also been as high as all the way up to the fall line, which is where most of the cities like Columbia and Raleigh and all that up the East Coast, that's the fall line. That's the first place you run into rocks. So that's why they call it the waterfall line. Anyway, so these cycles have happened, but we're kind of short-circuiting that cycle. We are getting this increase of sea level way before we normally would see that in history. And we can see just from observation, whether humans are causing it or not, I think is not the issue. It's happening. We're seeing sea level go up in the data, the water level data, and and it's being confirmed by satellite altimetry because we'll be able to monitor it all over the world. It's going up and down. So the answer is, it's happening. Are humans causing it? The greenhouse gas, the CO2 concentration is what's driving the temperature up. And if you look at where is that coming from versus naturally versus anthropogenic, then it's overwhelming evidence that we are causing, since the industrial age, that CO2 level has gone up way faster. And we do have events like volcanic eruptions that contribute to CO2, but they also can cool the planet because of the ash and everything too. So, I mean, it's a combination. That's why it's so hard to model. There's natural variability for sure, but in the long term, we're seeing that cycle short circuit. The only thing I would mention, are humans moving into more dangerous areas? Is that why we're seeing issues? And that answer is yes. I mean, part of we see the billion-dollar disaster number keep going up. Is that because there are more disasters and they're worse, or is it because we have more people living in the places where there's disasters, or we're building stuff that's going to get damaged, which is causing and I think it's a combination of both. We tend to live at the coast. There's I don't know what the percentages of the population lives at the coastal areas, but a high number, and then so you're just at a very dynamic area, and you're going to have damage. Mother Nature doesn't want us to put solid structures to combat erosion. Eventually, she's going to win and take back that land, and so we have to get used to that.
Yeah, so I did a lot of graduate work on paleoclimate, ice age climate, did a lot of climate modeling along those lines. When I think of cycles, the cycle that really drives home to me is the orbital cycles. They call them Milankovitch cycles, and those were really driving the ice ages, and water coming from the oceans and getting locked onto the ice as the glaciers grew. So those are really kind of the important cycles in terms of sea level changes in the geologic past. If you to look at what kind of orbital things do we have to have set up to basically pull water out and make sea level drop? Well, you need to have cool summers in the northern hemisphere, right? The winters are plenty cold up there, right? But you need to have the summers that are cool so that the snow that falls doesn't melt, right? And when I was looking at kind of what was going on in terms of these orbital cycles and looking at the energy at northern latitudes, it looked to me like we actually should be going into an ice age right now as far as the orbital cycles are concerned. That's the trend we're going on, but we're following a whole nother different direction, a whole nother trajectory off of what the orbital cycles are indicating. There's a guy named William Rudiman. He did a lot of work kind of looking at that deeper view. So anyways, I just thought I'd add that comment.
All right, so we have, let's see. Will the historical grids for Florida be available to agencies and universities in the summer? So it sounds like somebody's interested.
Yeah, so we've got a thing called Science Space, where we'll put out these grids, and we're actually, as soon as we get certain years simulated up, we're going to start putting them out there. So that they'll be out even starting before the summer.
All right, the next one is, have most climate models been able to keep pace with the unprecedented environmental change that we're observing in real time? What examples exist for models that have underestimated impacts?
I would say that, well, it's not so much the models. it's trying to predict the input to the models. That's where we've got kind of a lot of the uncertainty. Are we going to follow this one pathway or this other pathway, right? The models do a pretty darn good job if you can get the pathways right. And that's one of the reasons why we're saying let's do a 2-degree and 3-degree world. Let's not worry about the pathways, right? You can shift that around and figure out, 5 years from now they're going to have different pathways and so on. But anyways, the models are pretty darn accurate, and you can get the sense of that out of the weather models, how they can get pretty exact out of what's going on in the next week or so, and so on, get the climate quite well in the long term. Example models that have underestimated impacts. I don't think I could give a specific answer for a model that has underestimated impacts. There's some that are lower than others, but they generally, so let me back up here a little bit. When like CHNEP 3 came out, this first set of models, the way I kind of look at it is that they had all these climate models that people were working on. This one was used to look at the Arctic, this one was used to look at the tropics, this was used to look at this, that, and the other thing, and they basically threw them all on the table and said, here's our output. They weren't necessarily designed to do a look at the entire globe, right? They needed the globe, but they wanted to look at what was going on in the tropics. So the one for the tropics probably didn't do a good job for the poles, right? That kind of thing. And as we went from this initial group of modelers that were not focusing on global climate change, then these more recent models now are focusing on that, and so we're getting this convergence from that spread that originally was there.
I was going to just add one more thing about modeling, and you can think of it in terms of like weather models or hurricane models. There's a couple different ways. You can run a model once, and that's called a deterministic value, and says, okay, this is the track of the storm. This is where it's going to make landfall, so here's what the impact is going to be. And then what you'll see is, climate models do this too, you run an ensemble. You run different speeds, different directions, different intensity of the storm. You run it over different paths, and you come up with this whole range of outcomes. And you've probably seen the spaghetti models, when you look at the hurricane stuff. And then so you've created a whole probability distribution based on possible outcomes. And then you try to hedge your bets and say, okay, well, we're pretty sure the upper end of that is not going to happen, and we're pretty sure the lower end is not going to happen. There's that sweet spot, that mean. And I think that's where, yeah, you do get outliers where you get it underpredicts, right? You'll have storm surge models that do the same thing. But if you do it as an ensemble, you can kind of look at the probability distribution, and that gives you a better idea, so you can kind of figure out what the uncertainty is versus just one run.
And the other thing I sometimes see with the hurricane as an analog for selecting models is that you'll find that the forecasters will go like, well, actually, we think for our area, the European model is working best, right? Or this other model might be working best, so they kind of focus in on these ones that they've gotten confidence in. And that's what the Flood Hub and this whole kind of exercise that we're doing, the project that we're trying to get to. It's like, oh, which one of these models actually, they're kind of all over the place, but which is there one that we can say that I'm having more trust in this one?
All right, if we can go up just a little bit. All right, with seagrass loss at Ding Darling, this I believe is from Mark, you briefly mentioned how temperature affects algae. How significant do you feel reduced low temperatures and freeze events affect seagrass dynamics?
Well, I believe that probably that's a very significant factor. It seems like in the past we had more days in the range where it would actually be detrimental to algae growth, and maybe you had the algae diebacks at that time. But now we're seeing fewer and fewer days where we have temperatures that low. So I think that's one of the things that are driving the increase in algae that we're seeing at our sites, and also the fact that we have more hours in the range of maximum photosynthesis activity each year. So it just seems to be favoring macroalgae being the better competitor at some of our sites right now over our seagrass.
All right. Who is USGS working with and providing data to so communities can work on resilience in regards to flooding and rainfall?
Working with the Flood Hub. And really working with the water management districts. We do an awful lot of work with South Florida water management districts, and Carolina Moran is going to be speaking tomorrow, I think. Yes. Yeah. So we work with her an awful lot. She's on a lot of the calls, and so it's really, that's what we're here to support as far as the state goes, is like the water management districts, the state agencies, or so on that are resilient, that are dealing with this.
Engineering design and construction is critical for resilient infrastructure. How can we best incorporate these sea level rise and extreme weather models based in observation into design?
I can start on that. Yeah, it's a good question. So one of the things that we are working on, NOAA is trying to work more closely with, is ASCE. That's the American Society of Civil Engineers. And they're the group that puts out engineering standards. And they're like literally asking, like, we need a number, we need something to design to, we need to put that in the standards. And often it's, in an engineering world, you kind of have to do, you're looking really for one number, or at least a factor of safety or something like that, where you're like, oh, this can't fail, so we have to build it to this level. And the irony of the climate situation is this, we're not that certain, right? So you kind of have to change your model. They call it a risk management approach, where you're, if it can't fail, you have to use a higher scenario. If it can, then you can use a lower scenario. And then there's, of course, the whole cost benefit, because you can invest it. It's exactly like stormwater systems are not ever designed for the 100-year rainfall or 1%, because it happens so little that if you invested that much money into it, you wouldn't receive the benefit. But what they're starting to do, the engineering community, is to look at these scenarios, the sea level scenarios, and plan for that, and in some cases do worst case, and I'll put that into design, which would be, your first floor elevation being higher to accommodate an extra base flood elevation. But there's other considerations too when you raise the first floor. Well, if it's going to be accessible, the ramp angle has to be a certain amount, so that's more cost. And then also access. You can raise a building. We have a hospital in Charleston, a brand new children's hospital was built at MUSC downtown. They raised it. I mean, the first floor is higher, so it's not going to flood, but you can't get to it if the roads are flooded. So that one of the other hospitals in Charleston, Roper Hospital, is private, is going to move off the peninsula because of that. So there's design and buildings and all that infrastructure, but then there's also the access. So there's a lot to the equation.
Yeah. So this is kind of the question that we've talked a lot about. With the Florida Flood Hub meetings, right? How do you incorporate that? Now, for USGS, what we do is we basically provide the kind of root science. We give some of the gory details sometimes of what's going on. And then that's got to get translated into, how do you take that and pull out the numbers that I need? And that's what the Flood Hub is writing up now, and we're talking about it, and we're looking at for these certain return intervals, instead of looking at this range, do we have confidence in those points that are really out there on the edges? And there is really a good cluster around the central tendency, so we're looking at kind of putting out a report. So like for the state of Florida spatially, what would you use for these change factors, for example? You don't want one county over here using 1.5 and the county next door using 1.2 as your change factor, right? You want to have some kind of consistency, and what do we have the most confidence in kind of moving forward and providing guidance in that respect?
All right, if we can go down a little bit. So it says Northport received 23.5 inches of rain during Ian 2 years ago. They could get 24 inches of rain next year during an extreme weather event, right? Are the extremes factored into local models?
That's, that's what's called kind of nudging on these models, is that you try to set up these reanalysis so they have the timing or the pauses of these fronts when they stall out. That's the kind of thing that typically happens, is something stalls and it sits there and dumps, 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 right? And so that's the kind of thing that we're doing. The term is called nudging, right? So you try to match the observations as much as you can. Yeah, so we're trying to get that. Did I answer that question?
Yeah, no, I think that another thing that maybe you might want to touch upon is like there was a lot of, understanding and engineering and stormwater design about recovery times. And one of the things is with these more frequent storms, sometimes we're not having the system be able to bleed down fully before the next storm hits. And so there can be a compounding impact. And also just understanding the surface groundwater interaction about what's happening there. And I know that there's a lot of people now realizing we need to think differently going forward, understanding the frequency of these events are going to be likely increasing over time.
Yeah. I don't know if we're really seeing like hurricanes frequency is increasing, but the intensity is those are the kind of things that I've been hearing. But the whole kind of antecedent condition thing is definitely an issue. And are these, you saw this, what is it? I can't remember the name of the storm that hit Texas and stalled. Harvey just sat there, right? The same kind of thing. We also we're the Caribbean, so we worked in Puerto Rico. So you had Hurricane Irma come and skirt Puerto Rico, got everything all wet, and then Maria hit, right? So those kinds of things. And that's the kind of stuff that as we look into these future simulations, right, are we seeing things like these hurricanes get more intense or maybe more frequent in our simulations, right, because they can simulate the hurricanes? Or they're stalling, and that's to me the one thing that I've been kind of scratching my head about, because I've seen more and more of these hurricanes just kind of, they'll hit a front and then they'll just sit there, right? And that's where you got problems, right? I don't know if I answered the question, but.
No, I think there's so many different dynamics, the slowing of the storms, sometimes the iteration. I think with Ian, we had already an event before Ian that had already filled a lot of the systems, and then that event hit. So, there wasn't the capacity.
Right.
And I think that's a lot of lessons learned, which we're going to hear about more after lunch too, about things that people are thinking that need to be considered going forward that are different than what we've always assumed and engineered for.
And Ian, there were some intense hurricanes that were in the past decades ago where the hurricane was the size of the eye of Ian, right? They're just getting big. And that's the kind of thing where I'm talking about the intensity too. They're just getting big.
All right. One thing I don't think you've mentioned that I think is really interesting that maybe the audience would be interested if you feel ready to speak to it is that the atmosphere, as there's warming, it can create denser clouds, so that can contribute to rainfall extremes. Do you care to mention anything about your understanding of that?
So, as the atmosphere warms up, it can hold more moisture, right? And there's a relationship that we use called the Clausius-Clapeyron equation that looks at that, how much moisture can the atmosphere hold? And as temperatures goes up, that goes up, right? And what we're trying to do is, with some of these models, is we're using like physics equations like that to see did this statistical model go off the deep end and they're violating laws of physics, that kind of stuff. But that's generally the kind of discussion that I've been hearing a lot is that the increase in temperature is allowing the atmosphere to hold more moisture, and that can create more extreme events.
So is that going to be something that you're going to look at in your
Yeah.
continued modeling and
Yeah.
trying to understand those different, at 1.5 versus 2 versus 3, that would look at the atmospheric moisture as well?
Yeah, I wish Opie was here. He was hoping to come, but he's been spending an awful lot of time looking at exactly that, looking at the impact of temperatures having on the atmosphere ability to hold moisture. It gets a little more complicated than that because you get dynamics, and not that you can hold more moisture, but, can you move moisture in and out of the system too, right? So that the whole dynamics of what's called advection can come into play as well.
So it says, compounded effects of sea level rise make systems more vulnerable and could provide feedback mechanisms. Is this incorporated into the models?
The sea level rise models,
The compounded effects
yeah.
of sea level rise?
So one of the things that, and I'm not sure if this is going to address the question, but riverine and freshwater flooding versus coastal flooding, they were typically studied, and I would call them silos. You had hydrologists were studying river impacts, and then you have coastal folks, oceanographers doing sea level. What we're trying to do more of is, like John was mentioning, coupled models, is coupling, the riverine and the precip models with the water level models, like hydrodynamic 2D water level models of what's going on in the estuaries, because that's sort of where they come together, is a complicated thing. And yeah, so sea level impacts, if you have more sea level, higher sea level, you're going to increase the tidal prism. It's going to change the tides, how the tides flow through the estuary, how that saltwater wedge is going to go up into the fresh water. And there are examples where you have storm surge, for instance, in New York Harbor. It goes all the way up the Hudson River, all the way up to Albany. The tidal range in New York Harbor is the same at Albany Dam, 4 feet. Isn't that crazy? So that tidal wave goes all the way up that river, because it's a really deep river, so it doesn't attenuate. But that kind of thing. In terms of the projections, the sea level projections, it's really related to the global climate models, and so the feedback of what's going on locally. What we try to do there is to take into account if we know what's going on with the tides and the oceanographic currents, vertical land motion. We try to regionalize that as best we can. But are we getting all the feedback loops in there? Probably not. How it affects individual estuaries, that's a really complicated thing, because we got to be able to model what the future is going to look like and how that tidal prism is going to change and everything else. And then there's the what humans are going to do. Are we going to change the whole system by doing seawalls or changing the flow like we have done? That's why the Everglades were a mess to begin with, because we changed we channeled everything. So yeah.
Yeah, on the WRF model and all the models that we're starting to work with University of Miami and Florida State, one of the things that we're talking with the sea level people that are part of the Florida Flood Hub and saying, okay, in a 2-degree warmer world, 3-degree warmer world, what is the likely sea level? And so we would basically be inundating the models. That's part of it. The other thing is that these models, they have a land atmosphere model. So they do have components of the model that, allow the water to get into the groundwater system, and even simple groundwater models that will say that everything's saturated up. And that's one of the things that when they were simulating climate change or they're trying to do a reanalysis in the Midwest, until they got the groundwater right, they weren't getting the thunderstorms right? And that's even more important here. So we've got a groundwater model that's actually part of the WRF model, so we can tell that this is actually getting saturated conditions. It looks like we're getting close to our time here.
All right. I'm keeping an eye on the timekeeper, so I'm sure she'll let us know when we wind up here. If we can go up a little bit, I want to see if we have some more for Mark. All right, final question. Mark, maybe if you could go a little higher, please. All right. Lots of good questions, and of course, stick around over lunch. Our presenters will be happy to answer questions we didn't have time to get to. It says, have you looked at nutrients in the sediment and how that may have changed seagrass densities?
No, we haven't done that. We need to do that. We understand, there's a lot of dynamics we haven't yet looked at. But this was just our first go-around at it, so we will proceed.
I could just comment real quickly on that, is that we have another project of looking at continuous measurements of sediment coming down the Caloosahatchee and the St. Lucie River, and trying to get daily estimates or even hourly estimates of sediment transport. That's an ongoing project we have with the South Florida Water Management District, and that data would be handy once that's calibrated up.
Great.
Well, great. Well, help me thank the panelists. We very much appreciated them sharing the latest climate science with us. And with that, we're going to